So all credit goes to these folks over here, especially Dr. Sanchez. He has developed most of this content, all of it pretty much. So a lot of credit goes to them. There's a new chapter one for this, the newest version now that he made. And it starts off with this continue this definition, which is basically the continuum description of gas, which is a beautiful description over here. Now, what is this saying? Well, this is saying, let me get this correct because I don't want to mess up what he says. But we should read this actually. What am I doing? We should read this. This is straight from Dr. Sanchez's mouth. As a gas is fundamentally discrete medium composed of molecules of characteristic diameter dO, which is equivalent to saying 3 times the 10 to the negative 10 meters, separated on average by a much larger distance d, with d equal to 3.4 times 10 to the, oh my God, I can't say it, negative 9, power to negative 9 meters under a normal ambient condition. As a result, there are of the order 3 times 10 to the 16 molecules in a cubic millimeter of air. This enormous number of constituted particles constitute a key. Okay, so this is just saying what when there's a big molecule difference. I'm going to speed this up like 10 times in the actual video, so we should be good on actually reading this. Clearly, it is hopeless to attempt to describe the macroscopic dynamics by tracking the fate of each individual molecule. Such a description requires, in principle, the integration of Newton's second law for every molecule to determine its position and velocity, while accounting for intermolecular force and collision. The resulting computational task is utterly intractable, well beyond the present and foreseeable computational capacity. Instead, the study of compressible flow adopts a different view, based on so-called continuum hypothesis. So clearly, that is an important thing. That's the last sentence of the whole thing. As you know, usually what the most important thing is the first sentence, which is this stuff. And there is the last sentence that always shows important stuff in any textbook. So continuum hypothesis is important, I think. In the following discussion, we introduce the concept of a macro length scale, L, defined for a given flow field as a characteristic distance over which significant variation in the flow properties occur. Okay. Okay, defined for a given flow field as a characteristic distance over which significant variation in flow property occur. For example, in cases of flow over airfoil, the chord length and naturally emerges as equivalent macroscopic length scale. This length scale is central to the discussion of the flow field as it determines the level of spatial resolution required to attain a realistic repetition of flow. In the airfoil example, where velocity variation occurs over distances order 1 meter, okay, very big, much bigger than the distance of the molecules. It would suffice at the distance and time to specify the velocity vector as a separate point by 1 centimeter, or perhaps 1 millimeter, if more accurately described as desired. The observation moderates an approach to fluid motion in which the fluid is conceptually divided into small parcels called fluid particles, with respect to which quantities such as velocity, density, and pressure are defined. Each fluid particle is centered at the position x at a time t, and its size is assumed to be much smaller than the macroscopic length scale of the following under consideration, flow under consideration. Under the assumption the flow properties can be represented accurately as my battery's low. A continuous function of x and t, defined in which the properties of individual particles, the assumption of macro flow may be treated as continuous function despite the underlying discrete molecular nature is known as a continuum hypothesis. This hypothesis, underlying which fluid mechanics is also employed in other areas such as elasticity. To investigate the condition of continuum is valid, it is instructive to consider the definition of density for fluid particle as this. Okay, we have something. Oh, that's beautiful. That's centered at the exposition of density is defined as this. Wonderful. We have our definition. So what does that tell me? Well, we see our V1 and V2, and he is saying that there's nothing here, and suddenly there's 1. Therefore, it suddenly pipes up, and then it goes bigger and gets 2. But before that, it doesn't have anything gaining, so it goes downwards and upwards, downwards, downwards, and it goes like this. I do not know what this region is saying. It's going. Oh, that's not following my cursor. My apologies. Let me just fix this real quick, and let me redo that section again. So all I was saying is that we start with nothing. We start with nothing, and that's over here, and we slowly get up to here, which has 1, as shown over here, and then after that, another track, it gets to V2 and goes downwards. And it has this effect until it goes to here, the sufficient L length. I do not know what's going on over here. When it flows off, I'm going to read more and see what that tells me. It hasn't really told me yet what that means afterwards. By description to be meaningful, the value of density must be independent of the chosen volume, this. So the density at position x and time t can be defined uniquely as this. Okay, that's true. To assess whether this requirement is satisfied, figure I1 shows the variation of this, yes, as a function of a characteristic particle, the size, fluid particle volume, square root of cubic square root, that's right. When the size of the fluid particle is much smaller than the characteristic intermolecular distance d, the particle is very likely to be empty, and the corresponding density this is identically 0. As such, the particle size increase. Critical value is reached at which the first molecule enter the particle, resulting in an abrupt increase in the density. For a slightly larger value of the small fluid length volume, I should call it length because the particle is actually showing the length scale at the end of the day, right? The density, the density that then decrease at the volume increase until a second molecule enters the particle, inducing another jump. As the particle size continues to increase, these jumps become progressively smaller and even eventually negligible once the particle contains a large number of molecules. That is when this happens. In this regime, the density approaches a plateau plateau value that is effectively independent of delta V, thereby defining uniquely the density at position x and time t. This plateau persists as long as the particle remains small compared to the macroscopic. Like, here it is, L at the flow. Where L, however, the particle begins to encompass the flow with generally different molecular properties, and the density can no longer be regarded as a local uniform. Thus, indicates a well-defined macroscopic flow property based on the fluid particle concept, except if and only if the particle size lies in this range. The value continuum therefore hinges critically on this, which allows the introduction of fluid particle with well-defined properties. Okay. Well-defined properties. For air at normal ambient temperature and ambient condition, this is true. 3.4 times 10 to the negative 9 meters, and the most flow in engineering to satisfy this requirement, making them amiable to a continuum treatment. In contrast, in situation where L equals to L, D falls outside the domain of applicability of the continuum hypothesis. A notable example is provided by ratified. Oh, really? Ratified flowed around the re-entering vehicles in the upper. Oh, yeah, he did explain that. Where the mean distance between neighboring molecules become very large because space, they go re-entry, the molecules are less compact, you can't even breathe there anymore, and so forth, is what he's saying. Beautiful explanation. And oh wow, this explanation is, yeah. Okay, we'll go. The concept of a fluid particle allows us to define the density of a fluid as this. Beautiful. Subject to additional conditions, yes, which ensures that the discrete molecule nature of the fluid does not manifest itself at the microscopic level. Similarly, the fluid velocity may be defined as a mass average velocity of the molecules contained within the fluid particle. Okay, so I can read it, but I should probably write this one down because honestly, repetition is king. So what he's saying, first of all, is this portion over here. This portion over here tells you the density of a fluid particle. Yes. Which shows you that. And then velocity can be defined as a limit of delta V going to 0, a summation mi vi divided by summation mi. Okay, and I'm assuming what that means is that this 0 is not really 0. We're just saying 0, but in reality, we're saying, yeah, we're saying small fluid going small enough but not breaking the DO. That's what I think he's saying. Because look at this is much greater than that. Ensure the discrete molecule. So it's making sure that we still have acts like a regular fluid and not as distinct molecules that does this. After all, the speed of a molecule inside a cube, one of the molecules, if you measure it, can be as fast as the speed of sound, which is 343 meters per second, kilometers per second, no, meters per second, kilometers per second in, no, meters per second, I think, yeah. In normal air, ideal gas air. So yeah, beautiful answer, beautiful. It looks okay. Which corresponds to the velocity of the center mass of the molecule example. Okay, the total energy per mass unit contained in this is given by this formula where this is true. So over here we have total energy, we have the kinetic energy afterward, we have the vibrational energy, and we have rotational energy. Now I've seen rotational. Have I ever seen vibrational? I'm not sure if I have. I don't think I have seen it yet. So I hope I get to know it eventually. But for now, I only know rotational. Okay, obviously you have to divide by mass to get the beautiful equation over here, which tells you the internal energy E is a lot of, I forget sometimes E and what E means. But E means everything else. So in the world of fluid mechanics and everywhere, for example, there's certain things that are hard to measure. And in this case, it's vibrational and rotational of individual molecules, and they have internal energy, and that will define it as small case E per unit mass. Is what we will define. I'm trying to think if I'm saying something wrong because I'll be looking foolish if I said something wrong. Nah, I think I did everything correct. Hope I did. Okay, I hope I didn't make a mistake there. Yell at me in the comments if I made a mistake. All right, so-called internal energy distribution I5 is left to exercise for the reader. I5. Using the laws of classical thermodynamics, it is assumed that the process is sufficiently slow that the system can consider to be in equilibrium at every instant. A key result for homogeneous equilibrium system is that the thermodynamic state is completely determined by specific any two independent state variables. The remaining variables can then be computed from the appropriate equation of state. Compressible flow systems are generally not in thermodynamic equilibrium, with fluid properties varying both spatially and temporally. Nevertheless, the results of equilibrium thermodynamics are found to be approximately valid for most non-equilibrium states encountered in the compressible flow. Specifically, an observer moving with a local fluid field can describe the fluid state in terms of thermodynamic variables that are related by the same equation of state that applies to systems in a straight equilibrium. This idea, known as hypothesis of local thermodynamic equilibrium, can be justified vigorously using kinetic theory for gas. So, okay, okay. Just using molecular exchange momentum and energy to collision, which allows them to adjust the local state of molecular motion. Molecular collision does provide the mechanism by which thermodynamic equilibrium is established in the gas. Okay, so established in the gas, the average distance traveled in molecular between successive collision called the mean path free path no, free mean free path can be estimated by equating the volume sweep out by the molecular collision over here to average volume per molecule in the gas. This gives us this formula, and this is due to him assuming pi divided by 4 is about 1, which yields, for instance, the mean free path to be 4 times 10 to the negative 7 meters for air under ambient. Okay, something. So over here right now we have that, which I'm shocked by. That's really small, but I thought it would be like more. I thought it'd be nano. I thought more. Yeah, so interesting. For a gas system in which the mean free path is much smaller than the microscopic length to L, each molecule undergoes a large number of collisions before reaching regions with significantly different macroscopic property. Consequently, the fluid remains very close to equilibrium at all times. Correspondingly to the local value density and internal energy condition of a local thermodynamic equilibrium approximation whole is therefore the mean free path is much smaller than the length scale L. Is represented as called as a Coulson number. Okay, a new number I never heard of. Note that the criteria in I6 is generally more restrictive than those associated with the continuum hypothesis equation 1. Okay, I1. Okay, that's fair. Okay, so it's more restrictive for certain reasons or not. Let me. Oh, and now we joined. Okay. Equation of state is next. Okay, equation of state. Let's do it. Equation of state. For the continuum hypothesis, we have been able to define the flow velocity v together with the density and internal energy by further incorporating the assumption of local thermodynamic equilibrium. The remaining thermodynamic variables can be determined through the approximate equation of state. In what follows, we shall adopt the perfect gas model, which neglects intermolecular forces and assumes that interactions between molecules occur solely through elastic collision. The equation of state for a perfect gas is the following: P over density equal RGT. And that doesn't help me if I don't see what they mean. Pressure divided by density equals the R, which is considered a specific gas constant, and the temperature. Now, molecular weight is important, but yeah, you get it. And I think we're good. Yeah. For thermally perfect gas, changes in internal energy dE and temperature dT are related by thermal equation state. Yes and yes. Where specific heat at constant volume dT, d temperature equals it, which may be generally dependent in temperature. We shall further assume that the gas is categorically perfect, that the specific heat as constant integrates yields a perfect simple linear relationship. Okay. 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 I think you can see my next useful additional thermodynamic variables. Okay. All right. There's a few more I need to put down. Oh, a lot more. Oh wow, a lot more. Okay. I didn't expect this much more, but we have tons to do. And I think my roommate's coming in, so I'm going to turn this into a 2-part video then. If he comes in, I'll pause the video real quick. I'm going to stop the video real quick, edit it, and do the second part. Yeah, he's coming in. Okay, I'll stop it real quick. Anyway, you can look at what we're trying to do. We'll do this later. I'll use my mouse instead. This is clearly just using H, right? And plugging this in here. I'm pretty sure it's H equal EP. Oh, my handwriting is bad with a mouse. But we're gonna have to finish it this way because I forgot to recharge it. P over density, right? And also I didn't buy the battery pack because that's gonna work with my mouse. Okay, anyways, and then this I believe is EV dt. I think that's what they did. There's no way they didn't do anything like that. Yeah, EV dt. So, and obviously this is integral to get EV t. So H equal EV t plus P over density. I'm pretty sure that's what they did. And then this is left, right? How would you get that? Well, ideal gas law. So this is going to be equal to EVT plus TG RG T. And then this is going to be equal to parentheses EV plus RG parentheses T. And then that's what you get over here. And we all know this equation over here where we have CP, wait, minus CV equal RG. When this happens, you can mute it to get this. Let me just pause now. And then we see that this then equals CP over T, which equals H. Yep. Over here, yes, alpha equal CP minus CV. That's true. And this is adding, I believe, the H in it over here. Just doing this and putting it into here. And then so forth. And now it's 11:30. I need to go to sleep. So I'm gonna stop